copy on it. Oh, now it has like that little thing on the end. I hate that. Oh, there we go.
Whenever you want to get started.
Okay. So our first paper was machine learning at Facebook, understanding the inference at the edge. So machine learning provides a wide range of capabilities that drive many aspects of user experience, such as ranking posts, content understanding, object detection, and tracking for augmented and virtual reality, and speech and text translation. Facebook currently trained on customized data center infrastructure, but they are working to bring machine learning inference to the edge, which is a technique by which smart devices can process machine learning / data locally. Right now, user experience is improved with reduced latency and becomes less dependent on network connectivity, and this enables many more applications of deep learning features. This presents opportunities and design challenges in order to enable machine learning and inference locally on smartphones and other edge platforms. Right now, Facebook focused on providing 2 billion monthly active users the best possible user experience. They are executing inference, which is the process of running live data points into a machine learning algorithm on the edge, makes certain deep learning services possible. For example, Instagram features that involve real-time machine learning at the image capture time. And Facebook has been proactive in developing tools and optimizations to enable all models and services to execute across observed performance spectrum. However, there is a large performance variability effect in the real world, such as only a small fraction of inference currently run on mobile GPUs. Inference sees limited co-processor use today as a result of close performance between CPU clusters and GPUs, as well as immature programming environment, and many unique challenges stem from the diversity of mobile hardware and software not found in controlled data center environment.
So looking at a survey of the devices that Facebook runs on, Facebook's neural network engine is deployed on over 1 billion mobile devices, which is comprised of over 2,000 unique SoCs running in more than 10,000 smartphones and tablets. So there's no typical smartphone or mobile SoC or system on a chip for this to be able to run on. In production, smartphone hardware is also extremely fragmented, and this is especially true with Android devices. Diversity comes from a combination of the multiple IP blocks in an SoC, and there are over 25 mobile chipset vendors. So each mixes and matches with its own custom designed components with IP blocks licensed from other companies, making this extremely difficult to focus on. Mobile CPUs also show little diversity. The general availability and programmability of CPUs makes them the default option for mobile inference. However, research has shown that CPUs have a long life. So in this graph, you're able to see a breakdown of the year smartphone CPU cores were designed or released, and 72% of primary CPU cores being used in mobile devices today were actually designed over 6 years ago. And in 2018, only a fourth of smartphone implemented CPU cores designed were in 2013 or later. So this poses a new real challenge for systems and computer architecture researchers. Proposed mobile hardware optimizations and accelerators need to consider the long CPU lifetime. The performance difference between mobile CPU and GPU/DSP is also very narrow. There's a high performance GPUs continue to play an important role in the success of deep learning, and it may seem natural that mobile GPUs play a similar part for edge neural network inference because of the desktop use, although today nearly all Android devices run on mobile CPUs due to the performance limitations of mobile GPUs, as well as programmability and software challenges. Mobile GPUs performance is bottlenecked by limited memory bandwidth capabilities, and unlike high-performance discrete GPUs, no dedicated high bandwidth memory is available on mobile. Mobile CPUs and GPUs typically do share the same memory controller as well, which is competing for the scarce memory bandwidth, which is not a good pro to have either. So coprocessors, the DSPs and the NPUs also have programmability challenges, and Facebook takes a data-driven design approach, and the difference in SoCs makes it inordinately challenging to perform fine-grained device SoC-specific optimization. These diverse SoCs have a significant programmability challenge, and it's difficult to deploy performance application techniques to SoCs that are implemented with different versions of device drivers, scopes of memory granularities, and consistency models. DSPs face the same challenges as GPUs as well. The compute DSPs are available in only 5% of what the Facebook apps run on, and vendors are adding vector and compute DSPs, but it's likely to take many years before it's even seen. NPUs are exceptionally amenable to hardware acceleration as well, and relatively few NPUs exist today, and fewer are programmable by third parties, but there may be an inflection point. So machine learning at Facebook is obviously very important. Facebook puts in significant engineering efforts into developing deep learning features for mobile platforms. And this is just an illustration of the execution flow of machine learning, but we're going to get a little deeper into that as well. So here are some machine learning models and frameworks that Facebook uses. Facebook did develop several internal platforms and frameworks to simplify the task of bringing machine learning to Facebook products. So the big one is their Facebook Learner, which is a machine learning platform that automates many tasks such as training on clusters, but they also use Cafe2 and PyTorch as a set of distinct learning frameworks. Cafe2 is optimized for production scale and broad platform support, and it provides cutting-edge mobile deep learning capabilities across a wide range of devices and is deployed broadly through the Facebook application family. It's also deployed to over 1 billion devices. 75% are Android-based, and the remaining are iOS. PyTorch is conceived with flexibility and expressibility in mind, allowing researchers to fully express the design space, where PyTorch 1.0 combines the production scale of Cafe2 and the research flexibility of PyTorch. So DNN inference at the edge. Smartphones are capable of realizing deep learning in real time without relying on the cloud, but there are also limitations. They have various resource constraints, including power, memory, and compute capability. And as a result, mobile presents both an opportunity and at the same time a challenge for machine learning. Depending on the application and products and domains, Facebook takes different approaches. So here's their mobile inference execution flow that Facebook uses. They start off with features being collected and selected for a machine learning modeling task from their Facebook Learner feature store, which is a registry of pointers to data sources, features, and models for training and inference. Then a workflow describing architectures of a model and steps for the model training and evaluation is built with Facebook Learner Flow, which is enabling workflow execution and management. And then lastly, they export and publish the model so it can be served in one of Facebook's production inference tiers. Although before the models are deployed for edge inference, there are optimization techniques that are used, such as quantization, k-means clustering, and execution engine selection. It can also be applied in the optimizer. So horizontal integration is something that they focus on with making inference on smartphones. Mobile inference is primarily used for image and video processing, and inference speed is typically measured as the number of inference runs per second, where inference time is used for latency-sensitive applications. Cafe2 exploits performance optimization opportunities before models are deployed onto mobile platforms and ensures fast model transmission to the edge by implementing specific features. It applies commonly used techniques such as pruning and quantization to aggressively cut down the size of DNN models while maintaining reasonable quality. So an example that they used was with their smart cameras for the AR reality example, and it's designed to add intelligence to cameras, processing images directly on an edge device. And this feature improves user experience by reducing latency and bandwidth usage. The advanced machine learning techniques are also applied to estimate and improve the quality of photos and videos from various Facebook servers to understand digital content locally, which is directly on those smartphones. A challenge with this, though, is the large computational demands for delivering real-time inference. And to do this, they need to train mobile-specific models, compress weights for transmissions, and execute quantified models. To lessen this cost, though, models can be compressed using a deep compression-like pipeline, where quantization is also considered. And to improve inference performance, some of the models are processed using an 8-bit fixed point data type for the weights. So some DNN model performance across a wide spectrum of smartphones. And we're able to see this on this graph here with two Facebook DNN models, classification and human pose estimation across multiple generations of smartphones in different performance tiers. And when computing the inference time speed up between the latest generations of smartphones, between the low end and high end performance tiers, we see a much higher performance speed up for smartphones equipped with more abundant resources. And you're able to observe that the performance tier does not always directly correspond to the inference performance. And the newest generation of smartphones in the low-end tier offer a competitive inference performance as that in the mid-end tier for both DNN models. So they also focused a lot on vertical integration with processing VR inference for Oculus. And Oculus creates new forms of interactions by running multiple DNNs for tasks including hand, face, and body tracking. And models must run a steady frame rate that's 3 times greater than mobile image and video performance requirements to provide a high quality user experience, which is Facebook's main goal. It puts the performance requirements of VR platforms on the order of many hundreds of inference per second and creates a challenge for embedded devices. To overcome this, Facebook does take a vertical design approach. So some practical considerations for processing on mobile device is that performance variability is a practical concern for Facebook because it's a challenge to make guarantees on quality of service. Real-time constraints and model accuracy are often competing objects, and higher quality models take longer to process, but they do provide more accuracy. So some DSP evaluations, results, and analysis. This compares the performance, power, and temperature of the post-estimation model running on CPU versus DSP. And we're able to see the CPU implementation consumes twice as much power as the DSP in the beginning, but then thermal throttling kicks in, so the power consumption of the CPU implementation drops while still using 18% more power than the DSP. Thermal throttling has a significant effects on performance, degrading the FPS performance to 10 frames per second. And the thermal throttling, which you're able to see on this graph a little bit, it's kind of hard to see here, but through the dotted lines prevents CPU from operating at an acceptable FPS performance level. So some performance variability observed in the production environment is a key observation. Mobile inference performance exhibits significant variability even across the same device running on the same software stack. Facebook examines inference performance results internally using a small-scale smartphone benchmarking lab, and there is much higher performance variability in the production environment, which is likely due to higher system activities in deployed smartphones and the environment smartphones are in, such as the temperature or the number of apps that are able to run at the same time. Concurrent processes or background activities can also cause reduced contention, leading to performance perturbation. And smartphone surface temperature is also very important. Depending on how and where smartphones are used, the likelihood of thermal throttling is potentially much higher in the production environment. Process variation and battery aging are also contributions to performance variability to have representative performance results and analysis. It's important to perform in-field studies for machine learning designs and performance evaluations for mobile space.
So here we have a few key points or key takeaways from what Cassidy has talked about. So the majority of mobile inferences run on CPUs, and most inferences run on CPUs that are at least 6 years old. And the performance difference between mobile CPU and GPU/DSP is not 100 times. And programmability is the primary roadblock using coprocessors/accelerators. Coprocessors and accelerators are used for power and stable performance, and speed up is also often secondary. Accuracy is a priority, but it must come with a reasonable model size. Performance variability is a real problem, and researchers need to consider full picture and system effects. So in conclusion, deep learning brings many exciting opportunities, but diverse and complicated design challenges to the edge. It is important to have in-field studies in order to capture the performance variability effect in the production environment. And Facebook hopes to guide the community to better design and evaluate deep learning inference at the edge.
So,
Before you guys start, I just want to pause here and ask him.
yeah, sure.
The first one is about the paper itself. Like, I didn't get a chance to read this one, but it looks very interesting to me.
Yeah.
Why did you choose this kind of paper?
I think this one, I kind of chose this one more for us, and I chose it because it was Facebook. So I thought it was more like I could really see like, okay, this is what they're doing in Facebook, and I can actually like understand it in a way that I use Facebook as a Facebook user. So that was kind of my point of choosing it.
Yeah, as what I can see from this paper, there's a lot of details about computer architecture. Like it talks about 4 different architectures: CPU, DSP, GPU, and also neural network processors. And a lot of things like the computation throughput, time latency, and also the thermal effect. These are all terminologies from the computer architecture domain.
Yeah.
So, I know you're not from the computer architecture side, so it's surprised to me that you choose this kind of paper because it's kind of hard on you
Yeah.
to understand some details like this.
Yeah, it definitely took some time to understand, but once I started to
Yeah.
understand it, I had to read it a couple times and look over it, but then it started to get more interesting once I was understanding what I was actually reading.
Yeah, so
Yeah.
I like the key takeaways you have at the end to
Mhm.
kind of summarize everything. One suggestion I can give to you is like when you organize a public presentation, you probably don't want to have your slides too busy.
Yeah,
Otherwise,
yeah.
I mean, it's easier for you to read it off the slides, but for the audience, it's kind of you'll leave them to fatigue to catch up all this, contents in one
Yeah.
slide. You can think about moving them to like a backup slides or some review sections
Okay.
in this slide.
Okay,
That'll
yeah,
be really helpful when you deliver the public.
yeah, that makes sense.
And also connected to the slide that you have the graph on the thermal growing. Yeah,
This
yeah,
one?
this one
Yeah.
looks very interesting to me.
Yeah,
I don't want to know which line is represented for what hardware. So the lighter gray is for CPU, is that true?
yeah.
Okay.
I
And
think
the
so,
darker
yeah.
one, the black one is for DS.
Yeah,
Okay.
yeah. Yeah, it says dotted lines to see the thermal throttling. It's
Okay.
kind of hard to see that though with how small this
So
graph
how can
is.
you understand the two dotted lines for this segment, for this like the middle segment? What would does that mean the thermal throttling effects?
It's like in between those two lines is where it occurs.
Okay.
Yeah,
And you see the drop on CPU for
yeah.
the throughput.
It's really interesting
The
how
power
the
drops
effect
as
of
well.
it. Yeah,
And when power drops, the temperature also drops. But it comes back in.
yeah.
Is that something like automatically done by the CPU hardware, or is it done by a software, for example?
What do you mean from that
Like
question?
Is that a physical phenomenon? Is it
Oh,
bounded to the physics, or I mean, is it controlled by a software like a driver kind of?
yeah. I'm not completely positive. I think that's just like what happens when it gets put into these like situations with the thermal throttling.
Okay.
But yeah, I'm not completely positive though for that one.
Yeah, I definitely see the DSP is more steady.
Yeah.
But CPU drops and comes back up and then drops again.
Yeah. And it doesn't go back all the way to where it was. So
Okay. Yeah, you can move on.
okay, sounds good. Yeah, wasn't sure. Okay. So the next paper that we looked at was strategies and principles of distributed machine learning on big data. So as an introduction, big data and machine learning specifically, traditional machine learning is changing with the growing use of big data. There's an increasing need for higher dimensional and more complex machine learning models. And there are models with billions to trillions of parameters. And it requires storage and computational powers beyond a single computer. The rise of distributed machine learning as well. Machine learning programs are executed across research clusters, data centers, and cloud providers with tens to thousands of machines. And given P machines, we would expect P-fold speed up in the process. However, the reported time falls far below this mark. And as an example, deep learning on Spark has not yet achieved a 5-fold speed up using 10 machines. So speed and scalability is a big portion of distributed machine learning research. So looking in a little further with speed and scalability, the two methods that are being explored is faster convergence, which is measured by iteration number, and faster per iteration speed. So the need to ensure correctness as well as speed is with this. There's a major form of computing workloads on the big data will shift from database style to machine learning style. And for example, probabilistic inference, constrained optimization, and geometric transformation. And looking at the machine learning properties, there's error tolerance, which makes the model robust again against limited errors in immediate calculations. Dynamic structure dependencies, which is changing correlations between parameters, is accounted for to achieve efficient and near linear parallel speedup. And then non-uniform speedup, which is the difference parameters can convergence at different iteration numbers.
Okay, so expanding a little bit more on the properties Cassidy just talked about, error tolerance is important for distributed system design, as the system doesn't need to guarantee perfect execution, inter-machine communication, or recovery from failure, which is good because it's easier to do things approximately, especially when the resources are limited. And the dependency structure is important for speed. If the machine learning program dependency isn't respected, it can result in suboptimal scaling with additional machines, which means the speedup is less than expected based on the number of machines being used. And it can also lead to outright failure of the program. And then the third property, non-uniform convergence, doesn't have much impact on the distributed system design. So running complex machine learning applications involving terabytes of data and trillions of parameters on a single computer can take days or weeks. So to fix this, programs are parallelized by dividing the updates by either the data or the model. Dividing by the data is called data parallelism, where the data is partitioned and assigned to parallel workers, and dividing by the model is called model parallelism, where the model is partitioned and assigned to workers and updated therein by running parallel updated functions. And this requires scheduling, which helps with the selection of model parameters, and is only effective when each iteration of parallel updates is restricted to a subset of mutually independent parameters. And there are two types of parallelism, complementary, which allows for simultaneous data and model parallelism, and sometimes depending on the machine learning you're using, you need to use this. And then there's also asymmetric, which allows data parallelism. Data parallelism can be applied generally to any machine learning program on an independent and identically distributed data set. So here's an example using LDA, the latent derelict allocation. So here you can see the data in the model were split into 3 workers. And as the time progresses, the models move to different subsets until everything has been computed. Properties of machine learning programs together with data and model parallelism equals a complex space of design options, which leads to several important decisions such as data batch size for data parallelism, how to partition the model for model parallelism, when to synchronize model views between workers, step size selection for gradient-based algorithms, and the order in which to perform updates. So the people writing the paper suggested that a system interface is needed, and this will help facilitate the study of machine learning considerations and organize these considerations into a series of high-level principles for developing new distributed machine learning systems. And the system must consider how to distribute computation, how to bridge the computation and inter-machine communication, how to communicate between the machines, and what to communicate. It is important to understand the internal dependencies and how breaking these dependencies through naive parallelization will slow down convergence. So it's good that machine learning programs are error tolerant so that they can automatically recover from limited number of dependency violations. However, too many violations will increase the number of iterations required for convergence and cause parallel machine learning program to experience suboptimal less than p-fold speedup with p machines. So then we need to look into how to schedule machine learning programs, and we want to do this so that we avoid violating as many dependencies as possible. So this will prevent the progress per iteration of the machine learning program from degrading compared to the sequential execution. And we don't want to leave any of the P machines idle due to poor load balance, and this will ensure that iterations executed per second from P machines is as close to P times that of a single machine. And achieving both of these will result in a near perfect p-fold machine learning speedup. So here's an example using lasso. The parameter pairs are grouped into subsets shown here in the red blocks with low correlation between parameters in different subsets. And multiple subsets can be updated in parallel by multiple workers. This avoids violating dependency structures because workers update the parameters in each subset sequentially. So machine learning programs exhibit non-uniform parameter convergence. So the scheduler has an opportunity to prioritize slower to convergence parameters. And this can improve the progress per iteration of the machine learning algorithm. When using distributed clusters, stops will occur to synchronize/exchange parameter updates. So it's important to load balance the work on each machine so that they work at approximately the same time. This will reduce the waiting time. Load balance strategies that are predetermined at the beginning of the iteration often struggle from stragglers. So a way to fix this is to apply slow worker agnosticism instead, where the system takes direct advantage of the interactive convergent nature of machine learning algorithms and allows the faster workers to repeat their updates while we're waiting for the slower workers to catch up. Scheduling, prioritization, and load balancing are intertwined, so we can combine these functions into a single programmable abstraction to be implemented as part of the distributed system called structure-aware parallelization, or SAP. SAP can specify how to prioritize parameters to speed up convergence, perform dependency checks on the prioritized parameters, and schedule them into independent subsets, and load balance the independent subsets across the workers. SAP exposes a MapReduce-like interface with three functions. First is schedule, which allows small numbers of parameters to be prioritized and then exposed to dependency checks. Push performs updates in parallel on workers, and pull completes the running of the model. So here we have two theorems. The first one is SAP is close to ideal execution, meaning that the scheduling is near optimal. And the second is SAP slow worker agnosticism improves convergence progress iteration. So empirically, SAP systems achieve order of magnitude speedups over non-scheduled and non-balanced distributed machine learning systems. So bridging computation and communication for operation-centric programs, the exchange of states between workers needs to be executed perfectly and without error. This is supported by bulk synchronous parallel BSP model, which is a bridging model that provides an abstract view of how parallel programmed computations are interleaved with inter-worker communication. And so this will alternate between a computation phase and a communication phase, which is also known as the synchronization barrier. But this has a few disadvantages, such as workers have to wait for each other to reach the next synchronization barrier. So load balancing is critical for efficiency, but you can still have stragglers, which will impact things even if the workloads are well balanced. And communication between workers is not instantaneous, so the synchronization barrier itself can take a non-trivial amount of time. So instead, we look at asynchronous parallel execution, which is an alternative to BSP, where worker machines never have to wait for each other and workers communicate throughout each iteration. This usually obtains a near p-fold increase iteration throughput, but it suffers from decreased convergence progression per iteration. So the solution to this is using stale synchronous parallel SSP, which generalizes and improves upon BSP. When a worker finishes the first iteration of computations, it sends a signal that it completed the iteration, and workers may be stopped or allowed to proceed as SSP sees fit. If a worker is more than S iterations ahead of any other worker, SSP will stop the worker, and S is the staleness threshold. So there are a few conditions that this uses. The first is bounded clock difference, which is the difference in iteration counters on the fastest and slowest must be less than or equal to S. Timestamped updates at the end of each iteration. Each worker commits an update, which is timestamped in time T. Model state guarantees, which allows the local view is guaranteed to include all updates with timestamps less than or equal to T minus S minus 1. And read my writes, where each worker will always include its own updates in the local view. And this has a strong theoretical convergent guarantees for both data parallel and model parallel execution. So this uses continuous communication, and this can be achieved by a rate limiter, which queues up outgoing communications and waits for previous communications to finish up before sending out the next inline. And managed communication reduces synchronization delays, which provides a small speed up in overall convergence time. It's also important to prioritize bandwidth by focusing on communication updates that contribute most to convergence. This ensures that changes to important parameters are quickly propagated to other workers so that the effects are immediately felt. An SSP can be augmented by a prioritizer. Here we have two examples. Absolute magnitude prioritization, which updates parameters are reordered according to their recent accumulation change, which works well for machine learning programs that use SGD. And relative magnitude prioritization, this is the same as absolute magnitude, but the sorting criteria is the accumulated change normalized by the current parameter value. The paper also discusses two types of storage. The first here we have is centralized storage, which is a master view of parameters partitioned across a set of servers, and the workers maintain local views of parameters. Communication is asymmetric, so the workers send updates to the servers, and the workers receive the most up-to-date version of the parameters from the server. This is supported by the master-slave network topology. Second is decentralized storage, where the workers maintain a local view of parameters. The communication is symmetric, where workers send updates to each other. This is supported by peer-to-peer typology. So the next question the paper considers is what to communicate. They decide it's important to reduce the size of message by aggregating them before transmission over the network. And they note that typically computer cluster networks can at most transmit a few gigabytes per second between two machines. And since parameter synchronization occurs many times, the time required for synchronization can be a substantial bottleneck. So the solution to this is to use sufficient factor broadcasting, SFB, which is well suited to decentralized storage paradigms, but can also be applied to centralized storage paradigms for communication from the worker to the server. And SFB for decentralized storage is robust under SSP.
So looking at Patoon, it provides a generic distributed system for machine learning algorithms running on big data. It runs on compute clusters and cloud computing, which is supporting from tens to thousands of machines, and provides programming for interfaces for C++ and Java, while also supporting Yarn and HDFS to allow execution on existing Hadoop clusters. It also features a machine learning library with over 10 ready-to-run algorithms, which include classic algorithms such as logistic regression, k-means, and random forest, and newer algorithms such as supervised topic models, MED-LDA, deep learning, distance metric learning, and sparse coding. So in conclusion, and in the future, Patoon might become the foundation for machine learning distributed cluster operational system that provides a laptop-like experience for programmers. It will also definitely require new systems such as containerization, cluster resource management and scheduling, and user interfaces to be developed, which are necessary steps to reduce the substantial human or operational cost of deploying massive scale machine learning applications in a data center environment. And then we have a slide for questions.
First, may I know which year is this paper published?
I'd have to look at the paper
Remember that,
to
yeah.
check, yeah.
Yeah, not sure if this project pen is still like active. I heard there are some hurdles. Do you know the authors? Where would they come from?
No, I don't
Okay.
remember the authors.
Yeah, so it's interesting that you mentioned about the stragglers. Can you go back to the slide?
Which one? It's probably towards the beginning.
Yeah.
That looks like
Anyway,
that's too
so
far. Yeah.
How do you define a straggler? Is that like slow machines?
Yeah, anything that falls behind during execution.
Okay, so then you have to give like a threshold, right?
Mhm.
By how many seconds they're left behind, and you can define them as straggler. Is that the case, or how do you quantify like how
So
many stragglers are
in
there?
this, they kind of just defined it as anything that falls like substantially behind. They didn't really give like a specific like threshold.
Okay.
But using the staleness one, that does provide a specific threshold,
Right.
so that it will stop after, like if the slowest one is farther behind than the fastest one by that S threshold.
Do you know the reasons why they become stragglers?
Probably just like whatever's happening on the machine. There might be other stuff running in the background and other things like that that can cause it to slow down.
Okay, that's not something to do with like the workload partition.
No, I mean, if it's poorly like balanced, it can obviously, like if one has like 80% yield and only is 20, it's going to be slower on the 80%. But if it's well balanced, usually it's, if like Cassidy and I are both running stuff and hers has a bunch of other stuff running, hers is going to be slower than mine.
Right. Do they have any layers of workload? I mean, data balance, like data balance, I don't know, mechanism to ensure that each node, each worker node has like equal amount of data to work on?
They didn't go too much into load balancing.
Okay. All right. I do see that there are a few slides that talks about the diagrams. You have master slave structure and
Yeah, yeah. So here you see the centralized storage. So the leftmost one, it has the worker sending the update to the server, and then the right sends back the full parameter matrix, and then the graph on the right, that's the
Yeah, so
master
you see
slave.
the partitions as a red block for each
Yeah.
worker. I'm just curious about how they're going to ensure the data are equally, like an equal amount.
Yeah,
Like also, it really depends on, for example, let's say we're going to distribute image classification tasks across like 2 servers or 2 workers.
Mhm.
On the surface, it might be reasonable that if we divide the images by numbers, let's say worker 1 got 10 pictures, worker 2 also got 10.
Mhm.
But the reality is each picture can be with different size.
right.
And you don't know about the information until you start to work on those.
Yeah.
So how do you guarantee that the 10 pictures I got are the same amount of the computation I need for the other kind of, right?
Yeah.
So this is kind of like looks like neat to me at this point, because there's no way that you know about that before, even before you guys start on computation, right? And
Yeah,
also like the model partition, it also goes the same way. Like some parameters, they need to be more frequently tuned. For example, if you're working on a DNA model, if you're, say, my model partition is, so work on the layer 1 of my neural network and you're working on layer 2, then it's not just how many parameters I have, it's also about in what layer you should be working on, right? So the first layer definitely got a lot of parallelism. Like you have a lot of the vector to the matrix bigger than the second layer, because after each layer you're going to trim the data and do map spooling and all this stuff. So to me, like there's a lot of information which is not revealed from
Yeah.
the picture.
yeah, they definitely left like how to split them out of the paper. It would have
Yeah.
been interesting to know like their thoughts on that. 'Cause
Right.
they didn't, the way the paper sound was just kind of like, oh, you should look at like, this is the things people need to consider. So it would have been good to include
Right.
that.
Because I've been working on very similar questions, research problems in the past. I know there's a lot of things you have to consider as well. And can you go to the next picture? This one is the deserialized storage. Is that for the SSP, or is that targeted for any?
I think it's just like in general
Okay.
graphic of it.
So do you also review any information about how do they communicate the model copies to each other?
Just that like in this one, the workers just send the information to each other. They didn't really go into like
What kind of
how they do that. Yeah.
Yes. So the problem is here, you can't just say, now give you my pickle file. That's not the case. It has to be, there's a lot of stuff you have to do before you send the data into the next worker, like serialization, deserialization, like how to compress the model before you send it out. And like it's not even consider the overhead of doing those steps. I don't know.
Yeah, they definitely simplified a lot of things
Yeah.
in the explanation.
And also, like, if let's say worker 1 sent delta to worker 2, and worker 2 also sent delta to worker 1, do they explain the algorithm that happens in between, like how to synchronize those deltas? Like, say, worker 1 say I have to change 10 hyperparameters, and worker 2 said I have to change the other 10. Now, how do they aggregate the deltas together so that they can reach to a consensus across all the workers?
Yeah, they don't go into that.
Yeah. Yeah, to me, this is like a very general and
Yeah.
overview kind of paper. It's not going to be very helpful to understand the details inside. Can you do a quick search? I think this is one of the papers I choose from for the paper pool, right?
Yeah.
Yeah, this is one of the papers
Yeah,
you
so
have,
what
yeah.
was the name of the paper?
Strategies and principles of distributed machine learning on big data.
It was paper 11. I think we did 7 and 11. I just don't
Yeah.
remember which one was which.
Maybe 7 or 11.
Oh, your time is fine. I mean, that's a journal paper. I think it needs to be very generic, general
Yeah.
introduction to techniques. Okay, that's good now. I like the fact that you, this is a very long paper to read, and you kind of extract the most important things for the audience to know and hide some details that you're not able to catch up, even though if you have it on the slides. So if this is a different setting, for example, this is not a class setting, if you're going outside for a paper presentation, you probably want to show more details about the design, the internal designs, like for example, the LDA diagram you showed me. I know there's a lot of math behind that. You probably want to just skim through some of the key points, just behind the current, so that the audience will be able to know the meat and potatoes of your design. So, but yeah, so I think it's a very good presentation. The other thing, I forgot what I want to ask. Yeah, but so yeah, so for the tenant, that's a software, right? So that's like a distributed architecture for running machine learning in parallel. Did they talk about anything about like how do they integrate with, for example, Spark and Hadoop?
It briefly said they work with, like it works together with it. This was like less than half of a page that they spent on this. So it was just a real quick at the end. Oh, by the way, this exists.
Okay. So I think that's their main purpose, right? So they probably have, if that's not a review paper, then that's probably one of their designs. So in the research field, people first publish conference papers for certain software like Canon, and then they write another one like a continued research in a journal paper format, so that you can compare this design with other existing platforms and compare the pros and cons horizontally. So I think this is probably the order. So the author here for this paper is probably the author for Canon. Yeah. Anyway, so yeah, that's overall very good presentation. So do you think that's something useful for your study to the course as well? Like that, when you prepare for the slides and presentation, does that help you to understand the concept of the course?
I didn't feel like anything in this course, like in this paper specifically related to the course. Like obviously I recognized like yarn and HDFS and like some of the names, but we didn't do much with like distributed systems. So it was like a different aspect. So it was like extra information that I got to learn.
Yeah. So that's something I want to know because I designed this paper presentation section for, allowing you to read some papers and broaden the views.
Yeah, and that's definitely what it was. It was extra information that we got to learn.
Okay. That's cool.
Yeah, it was definitely really interesting too. I enjoyed after the first read through. The first read through was hard, but then when I started to understand it, I enjoyed learning about it.
Okay.
So yeah.
All right. Okay, I think that's it. Good job, as a team. I like you have, especially for the first paper, you have the key takeaways by the end. That's going to be very useful. And whenever you do presentations, you're going to have that section.
Yeah.
That's going to be a pretty important part. All right. So then I think for this Wednesday, we have the
Yeah.
data science.
This Wednesday is the capstone.
Yeah.
Yeah.
So Dimitri will come here to join us.
Oh, I wasn't sure. I did ask Lisa Kennedy and Doug Sheasley, and we can send them a calendar right for it too.
Oh, okay, cool. Yeah, I talked with Deborah last week about the another potential project for.
Yeah, she's telling me about that.
Yeah, so we're planning to do like a LinkedIn data scraping.
Yeah.
A lot of job hunting website now have very limited data accessibility. Like they want to avoid people scripting their website. But I think I found a way to become like a LinkedIn developer so can have APIs to access that. But that's not something you have to do.
I had a question about
Sure.
DS420 homework 5.
Mhm.
Mostly just about the helper file.
Okay.